Thanks. Good afternoon, everyone. Today I am going to present my research area. My research topic is to build a 3D map for highly dynamic system using sensors like LiDAR and IMU. My presentation is divided in 4 parts. First, I will give a brief introduction of my work, and then I will explain the methods which we used to build a 3D map, and then I will show simulation results and experiment results. 3D map is most important part of any robotic system. Here you can see in figure 1, a drone is used to deliver a package at Amazon, and in figure 2, a driverless car is shown, and in figure 3, a robot is performing some task to transport some materials. Have you ever thought how these robotic systems, these drones and driverless vehicles move from one place to another place, how they navigate in environment? It is because of this 3D map. What they do, they build a 3D map, and with the help of that 3D map, they navigate in environment. There are many sensors and methods which are used to build 3D maps. Here we use 2 different kind of sensors. One is IMU, which is Inertial Measurement Unit. This sensor consists of 3 sensors. One is accelerometer, which measure the accelerations. Other is gyroscope, which measure the angular velocity of body, and third is magnetometer, which measure the magnetic field. These sensors provide very accurate short-term motions, and it can give very high frequency data. Other sensor is LiDAR sensor, which is used to build a map. LiDAR sensors emit light waves continuously, and when these light waves bounce back by some objects or walls of surroundings, and it use the time which is taken by the pulse to return back to calculate the distance, and with the help of that distance it measures the map. It is invariant to light condition. It means it can be used in dark environment or at night to build a map, but it has some limitations, such as it is sensitive to surroundings, it has some motion distortion problems. So what we are doing, we are fusing both information of 2 different sensors to get more accurate, very precise 3D map. Methods. Our method consists on 3 major modules. One is inertial odometry module, which is used to calculate the rotation and the displacement of the sensor. Mapping module, which is used to build map, and mapping correction module, which is used to minimize the effect of noise on map and to get more precise map. This is the overall block diagram of our method. In inertial odometry module, we use IMU, which consists of sensors, gyroscope, accelerometer and magnetometer, and we implemented a complementary filter to compute the rotation. And we know rotation can be represented mathematically by 2 different ways. One is quaternion attitude and other is roll pitch here. So after getting the rotation angle by using inertial odometry module, it is used as the input in second module, mapping module. In mapping module, the LiDAR is present, the rotation base, and this rotation information from IMU is used to build a map, a 3D map. And in this module, the rotation information is used to transfer the LiDAR information from moving LiDAR frame to a very fixed world frame. And after that, we use a mapping correction module with the help of graph optimization by using G2O to get a very precise map. Here, the design of complementary filter is shown, where first the gyroscope data, which is angular velocity, is used as an input to predict the rotation by using the integration and some signal processing. And as we know, the gyroscope has some noise, so the rotation which is predicted by gyroscope also have some errors. So to correct or to minimize these errors, we use accelerometer, and we do some signal processing on accelerometer data and get a rotation angle with the help of accelerometer information, and use it as a corrector to the prediction which is predicted by gyroscope. And other same way, we also use magnetometer to correct the rotation angle. But magnetometer is affected by the magnetic field. If the magnetic field of environment is not very stable, then it is not good option to use magnetometer. So we use it as an optional. In mapping module, as LiDAR scan is continuously give a stream of scans in polar coordinate form in the plane of sensor, and we use a plane tilting system to rotate the LiDAR. Here we can see this is the rotating base, and this is our sensor LiDAR, and this rotating base is used to rotate this LiDAR sensor. And here the sensor and the rotating base, which is consist of motors and encoders, are placed together, and whenever the motor is rotating the sensor, it the snapshotter to send a request to laser scan assembler to start building map. And the laser scan assembler is shown here in detail, where the scan from LiDAR and TF data from IMU is used to transfer the scan to a fixed world frame, and this cloud data is saved in rolling buffer, and whenever it get a request to start building a map, it start saving this cloud data in buffer. When the rotation of this rotating base is complete, it send a 3D point cloud. Here the mapping correction module. The mapping correction module, first we do signal pre-processing, remove the invalid data, and then we do some plane fitting, and we extract the walls and the grounds and fit these planes in 3D environment, and then we construct the post-graph construction with the help of these wall plans and the sensor post, and after that we do post-graph optimization to get a very precise global map. Here the post-graph construction is explained in some detail, where post node is shown with these circles, and we use the walls and grounds as a node. So when from T0 to T1 sensor moves, and we got a relative pose which is represented by E1, and we build a measurement error, which is the distance of all points between the points and the distance of wall and the ground. And the purpose is to minimize this distance by optimizing the more precise 3D map. In simulation environment, we use a crane as a very highly dynamic system, and we attach the LiDAR and IMU sensor to the boom of crane. As we know, the crane the boom of crane is always in motion and it performs some task. So the task is to build a map, then the crane is performing some task and its boom is in rotation. We use two different environments. One is featureless environment and other is complex construction site environment. And we use Gazebo for simulation using rows, and we use RVs to visualization. Here is the results of our simulations, where we can see on right hand side, this is the Gazebo window where a crane is placed in an environment having only walls and sensor is attached on boom of crane and the LiDAR base is continuous in rotation. And on left hand side we see a 3D map which is built when the crane is performing some task. Here we calculate the error between the ground truth and our proposed method, and we find that the distance between our method and the ground truth is very less, is almost 0.15 meter average. To show the effect of noise on the 3D map, we use 3 different levels of noise, and we can see when we increase the noise level, there is a lot of distortion in the point cloud data. And the optimization method is to minimize this effect of noise of sensors. So here we can see on before optimization on left hand side, the point cloud is not very highly precise and accurate. There is a lot of distortion, and after optimization we get a very precise map. This is another environment in which we place a crane in a construction environment, and here we can see it builds a map when crane is moving. And this is one view of, and this is the experiments which by using a crane model. We attach the sensors IMU and LiDAR with the boom of crane. This is the LiDAR and this is the IMU, and these are the four sensors are communicating with the laptop and the systems. And here is the results of our experiment. Here we can see the crane is performing some task and the boom of crane is continuous in rotation, and here we can see a real-time online 3D map. And this is the zoom view of the 3D map. Thanks.